So today we're going to talk about complex polynomials. So just an introduction. So there's a theorem called the fundamental theorem of algebra, where every non-constant polynomial of a positive degree will have a root in the complex plane. So what this means is that the polynomial p of z, which is equal to a sub n z to the nth power plus a n minus 1 z to the n minus 1 power, etc., until you get to just a constant, is a polynomial of degree n, where a to any sub any number is in the complex plane, and a sub n is not equal to 0, and they are coefficients. So a is the coefficient in this case, so a can be any complex number. A complex number lambda such that p lambda equals 0 is a root of p. So this makes sense because this is the same in algebra. If you have any number that makes a polynomial equal to 0, then it is a root of that polynomial, except in this case, lambda can be a complex number. So there's always a complex number lambda such that p lambda equals 0. All complex polynomials of degree greater than 1 can be written in the form of p of z, a sub n, z minus lambda 2, z minus lambda 3, etc., z minus lambda n rather, where lambda n are all roots of p. Polynomials with real coefficients. So if all coefficients of a polynomial are real, and the complex number z1 is a root of p, then the complex conjugate of z sub 1 is also a root of p. So essentially, all of the complex numbers have to cancel out, meaning that this will leave us with only real numbers. And for all the complex numbers to cancel out, that means they have to come in conjugate pairs. So a procedure for finding roots, specifically complex roots. So we want to first try finding roots by using the root formula of a complex number. So this, going back, is essentially that point there where the complex polynomials of degree greater than 1 can be written in the form pz a n z minus lambda 2, lambda 3, etc. And then second, we want to try and find a complex factor. And then if we have one factor, then we want to perform long division to factor it out and repeat until we're left with a quadratic, which is a polynomial of degree 2. So once we have a quadratic, we will use the quadratic formula to factor the rest of the quadratic equation, and then just subtract these roots from z to find other factors. So yeah, basically we want to get to a quadratic, and then through long division, and then with that quadratic we can use the quadratic formula, and in this case we'll use complex numbers. Okay, so for an example, we're going to do a polynomial which has complex numbers in it, but for the extra example, oh, that's the same. Well, I'll change that, but the extra example has a polynomial which has only real roots, and we'll see that the factors of it, the complex factors, are conjugates of each other. So just look for that along with the updated presentation in the description. But we're going to work with this one first. So we have p of z is equal to, so I'm just going to rewrite it out really quickly here. You know what? I don't have enough room, so I'm just going to start over. Okay. Sorry. Pz is this. So we can see right away that a common factor is this 1 minus I so we can take that out. So what we're going to do is we're going to perform polynomial long division with that, dividing the rest of it. So what I'm going to do is just pull that out. Actually, I'll move it a little bit lower just so we have enough room. So we have the factor 1 minus I. And then we're going to be dividing, and I'll just say this is equal to z. So z cubed, just sort of shorthand and sort of helping with that there. So z cubed plus negative 1 plus 2i, z squared plus 1 minus I z minus 2 minus 2i. So we can see we've pulled out that common factor, and it makes it into a nice polynomial for us with decreasing degrees. We do want to keep this one not as z, just so that we don't have two z squareds, I suppose. So just performing long division on this. So this will result in, and this is just long division, so it's something that we sort of should have learned, but we'll kind of take you through the process anyway. So to get z cubed, we have to multiply this by, so just show you here, multiply that by z squared to get z cubed. So multiply that and we have negative. So z cubed minus z squared plus iz squared. And we're going to subtract that. And just going to get rid of that. So subtract that to get z squared I. That's all we're left with. And then bring this down. Plus 1 minus I z. So then we need another factor of zi. And multiplying that by this again is equal to z squared I minus zi minus z. And then we're going to subtract that, and we'll end up with 2z minus 2 minus 2i. Oops. Bring that one down, which gives us the 2 minus 2i. And then can multiply by, so to get rid of that, we'll multiply by z, which will give us 2z minus 2 plus 2i. Subtract that is equal to 0. So that means that we can use the quadratic equation for this here. So z is equal to negative I plus or minus root I squared minus 8 over 2, which is equal to negative I plus or minus root negative 9 over 2, which is equal to I plus or minus 3 over 2. So therefore, P of Z equal to Z minus 1 plus I, Z minus I, and then Z minus ZI. Okay, that's it for today. Thank you again to Luma and Google Keep, and as well to my professors who taught me this. And I hope you enjoyed, and I hope you benefited, and we'll see you again later.